morning, everyone. Am I audible? Okay. Okay. So, PDF I have already shared with you, I guess, in your group. Okay. CR group I have given. Okay. Filtration also I guess I have given. Yeah. For sedimentation and uh, filtration coagulation I have given. Okay. Okay, Shahini, you cannot hear me. Am I not audible clearly? It's not properly clear. So now is it clear? Is it clear now? I just change is same. Okay. What to do then? The settings are fine. I don't know why. Okay, just wait. Okay, just wait a bit. Let me change my headphone. Hello, can you hear me now? Is it better than before? Yes. Okay. Fine. Okay. Okay then. Let me share my screen. Acha, any one of you please tell me whether I have covered the flocculator part with you or not. this part have I covered with your section? Because this one I remembered I did it with section B. I have done section A. I have done or not? I forgot. So can you please, any one of you see and tell me whether it is done or not, or have I done or given your PDF of this one? The constituents of coagulation sedimentation plant have I covered with your section? Please write in the chat box if you remember. Yes, no. Okay, to no. Okay. Others, anyone remember? We did till construction and details of filter. Yes, Yulson, we have done that one, but in between when we are doing the coagulation part, did we cover up this one? Constituents of coagulation sedimentation plant after your coagulation part? I think no, because I have done that one with section B, I guess. Okay. Okay, so this one is between your, sorry, not between, this is a part of your coagulation aided with sedimentation. Okay, this was a part of your coagulation aided with sedimentation part. So this is just a constituent, like where you are performing the coagulation aided with sedimentation part. Okay, so where you will be doing that one is known as your coagulation sedimentation plant, or it is simply known as your clariflocculator. Okay, that this term clariflocculator is also known as your coagulation sedimentation plant. Okay, so for a coagulation sedimentation plant, there are four parts or constituents, or you can say. Okay, number one is your feeding device. Number two is your mixing device. Then your flocculation tank or flocculator, and the third one is your settling or sedimentation tank. Okay, so number one is your feeding device. So feeding device is like, wait, let me show you here. This one, okay, this one is a clariflocculator. This one is a whole one. Okay, the whole part, you can say, the whole machine clariflocculator. This is section view, and like here feeding devices are like this. Okay, so what it is done here in feeding device, there are two parts, you can say. One is your dry feeding and the other one is your wet feeding. Okay, so when you add coagulants to your water, you can do it either in dry form or you can do it in a wet form. Okay, so when you put the coagulant in a powdered form, okay, then it is known as your dry feeding. Okay, and that is done in a dry feeding device. And when the coagulant, it is, it is made into a solution and then it is mixed in the water, or it is put in the water, then it is known as your wet feeding, and that is done in a wet feeding device. Here the main work is to, in the feeding devices, the work is to just feed the coagulants to the water. Okay, so after adding the coagulants either in a dry form, a powdered form, or in a solution form, the that water, it is carried to the next part of your this clariflocculator, that is your mixing base device. Okay, that is your mixing device. So mixing device, again there are many types of mixing devices. Okay, and out of those, mixing basins are the most important ones. Okay, so in mixing basins, like you can see here, this is mixing basin. Okay, so one, again, mixing basins are divided into two types, you can say. Number one is your mixing basins with baffle valves, and the other one is your mixing basins equipped with mechanical devices. Okay, so first one, let us know the first one. So in baffle valves, okay, so you can see this diagram. This is a mixing basin. Okay, it is a, you can say, this is a rectangular tank. Okay, it is a rectangular sedimentation tank where you can see some baffle walls are put. Okay, you see this one, these are baffle walls. Okay, so these are put in a opposite direction. Okay, you can see one is put like this and the other from the top, again the from the bottom, then from the top. So what is happening actually, when the water is, you are pouring the water from inlet. Okay, the water is coming from here, then it goes like this. Okay, then it strikes this baffle, again it come up like this, again it strikes your this baffle. Okay, again it is going like this, again it is striking this, again like this. Okay, so it is continuously, what it is doing, it is continuously striking your baffle walls. Okay, so when this, water, it is continuously striking the baffle walls. So what is happening actually, a very violent, you can say, violent agitation is happening, and thorough mixing is done. Okay, while these waters are striking, with a very force, with a large force. Okay, so the water, it is, it is given a very thorough mixing. Okay, obviously we want the thorough mixing, because without the thorough mixing, we know that while after adding coagulants, we will not be able to get a gelatinous precipitate. Okay, but our main aim is to get a what, a gelatinous precipitate, or a flock, you can say, so that that flock, it will attract the other fine particles around it, and it will form a bigger particle, and then it will settle down. Okay, for that reason, this mixing, okay, the heavy mixing, it is done in a mixing basin with the help of baffle walls. Okay, so next is your, while the water, it is first, mixed with the baffle walls, then after that, that water, it is carried to the next unit, that is your flocculation tank. Okay, this is your flocculation tank. Here you can see this pedals, the circular pedals, you can see here, this one. Okay, so what here it is done, the water, it is when it is put to the next unit, that is your flocculator, the water, it is given a very, slow mixing. Okay, or it is given a very gentle mixing after a very heavy mixing, a very thorough mixing. Now the water, it is given a very gentle mixing or stirring, you can say, so that it can build up. Okay, so it can build up, and it can agglomerate the flock particles. Okay, it can agglomerate the flock particles, and due to that agglomeration, what will happen, the flock, it will become, it will attract the other fine particles, and it will become a heavy one. Okay, and it will finally settle down. Okay, but the settling down of the particle, it is done in the next unit, that is your sedimentation tank. Okay, but the slow and the gentle mixing, it is done by these pedals. Okay, you can see these pedals, it is done by these three pedals. Okay, so then after your gentle mixing, and after the flock has been created, then the finally, in the sedimentation tank, in the next unit, your flock is settled down. Okay, so this is a ultimate, this is our your final process of how the coagulants are being added to the water, and how the things are happening inside a clariflocculator. So this is just a constituent. You should know that these things are there, and with the help of this process is happens. Okay. So this one I think I have not given you this PDF, so I will share with you today. Okay. So basically, you just remember the process of how it is done, what is mixing baffle, and all these things. If you remember, then it is fine. Okay. But the whole thing it won't come, but still you should know. Okay. So this is your okay. So next, let me see what is filtration. Okay, we are in the filtration part, right? Okay, we have discussed about the slow sand filter and the rapid sand filter. Yes. So let us do numerical, one numerical related to slow sand and rapid sand filter. Okay. So this is your first numerical regarding your slow sand filter. So let's see the question. Design 6 slow sand filter beds from the following data. Okay. What are the following the data is given? Population is given to be 50,000. Your per capita demand, that means each person how much water he is having per day. It is 150 liters per head per day. Then rate of filtration is your 180 liters per hour per square meter. Then length of each bed is given to be twice the breadth. Also assume maximum demand as 1.8 times the average daily demand, and also assume that one unit out of 6 will kept as standby. Okay, so basically we have 6 units of filtration. Okay, filters we always in a treatment plant. There are six, not actually six, yeah, six, and one unit. If 5 units work, then one unit it is always kept as a standby. Okay, so that during operational fail, what happens? One that unit can be used as a helping unit. Okay, that unit can help. Okay, so here since your population is given and per capita demand is also given, and also it is given that you can assume the maximum demand as 1.8 times the average daily demand. So first we have to find out the average daily demand. Okay, so what was the formula for average daily demand? It was population multiplied by per capita demand. Okay, so it is 50,000 into 150 given. So 7.5 into 10 to the power 6 liters per day. Clear? So now after finding the average daily demand, you can now quickly find out the maximum daily demand. Yes. So maximum daily demand in the question, it is mentioned that you can assume it to be 1.8 times the average daily demand. So maximum daily demand when you find out, also the formula was also it was 1.8 only. Yes. So still in the question is mentioned. So you have to multiply it by 1.8 into your average daily demand. So you got it to be 13.5 into 10 to the power 6 liters per day. Okay, so now the rate of filtration is given as to be your in the question it is given to be 180 liters per hour per square meter. Okay, but your since it is given in hour and we need the unit in day. Okay, we need the unit in day because the other units you see your average daily demand is also in day, then your maximum daily demand is also in day. Okay, so we need to make the units similar. We cannot make it different units in a single numerical. So we need to convert the hour into day. So we are multiplying it by 24. Okay, we are multiplying the rate of filtration by 24, have got it in the answer into the day. Okay, so now the if you find, so suppose here it is given to design means what? You need the length, breadth and width, isn't it? So we need the length, breadth and width of the filters. So for that, what we need to find out the, first of all, the area. Okay, the surface area, if we can find out, then we can, the whole area if we can find out, then we can find the area for each unit, each filter unit we can find out. So if the total surface area we can find out. So what is the formula for total surface area? Your maximum daily demand divided by your rate of filtration per day. Okay, so maximum daily demand we already got it to be 13.5 into 10 to the power 6, and your rate of filtration also we got it to be 180 multiplied by 24. So the total surface area we got it to be 13125 square meter. Okay, so now in the question it is given that you need, no, there are 6 units and you need to keep one of them as standby. That means you need to design for 5 units. Okay, one is kept for a standby, so that means you need to design for the 5 filter bed units. Okay, so now since you need to design 5 units, so you can find out the area for each unit. Okay, how will you find the area for each unit? The total surface area you already got. Now you need to find out the area for 5 units. That means you need to divide it by 5. Okay, you see here. See here. Uh, since you in the here it is the area for each filter unit. That means 5 filter units. It is your 1/5 into total area required, and we got it to be 625 square meter. Okay, so now again, now that you have got the area for each unit, now you need to find out the length and breadth. But in the question it is given there, the length is equal to twice the breadth. Okay, it is given in the question. So you know that L into B is equal to your area, correct? So in place of L, okay, in place of L, you can put twice B, because in your question it is given L is equal to twice B. Then here one B is already there, so it will be 2B square. Yes. Then what is the area we got? We got it to be 625. Okay, we got it to be 625. So after that you can proceed it like this. Okay, you can easily find out the value for your width, and after finding the value of width you put the B value in your L. Okay, since it is given that L is equal to twice B. Okay, then first you got the value of B, isn't it? So now you can easily find out L. Yes, L will be your double, so it is 36. Clear? So you have designed the filter unit. Okay, so you can write the sentence like this, that use 6 filter units with 1 unit standby. It is already mentioned in the question. So each unit of size 36 meter is the length and 18 meter is the width, arranged in series with 3 units on either side. Okay, so this sentence you can write down. So finally your answer is 18 meter by 36 meter. Okay, so this is your ultimate answer. I hope you can understand. Okay, this is not a tough numerical. This is if you can remember the formulas of average daily demand and maximum daily demand. Okay, then you can find it out. Then next is, let me see. Then let's proceed to the rapid gravity filter 1 numerical. Acha, if this class ends, then you join by 10:15. Okay, the link, I will share another link. You join the by through that link by 10:15. Okay, so this one is your rapid, that one is your slow sand numerical, and this one is your rapid sand gravity filter numerical. Okay, you can see here in the question it will be mentioned. Okay, so design the approximate dimensions. Here also same thing, you need to design of a set of rapid gravity filters of you just see the words. Okay, you see the words what it is given. Design the approximate dimensions of a set of rapid gravity filters. What is a set? That means it is a tube, okay, piece of tube. So that means you need to design two rapid gravity filters. Clear? So for treating water required for a population, so everything is given. Population is given. The rate of filtration is given 180. Okay. Then the filters are related to work 5,000, rated to work 5,000 liters per hour per square meter. Assume whatever data is not given. Okay. So again, same procedure we will continue. Okay, same procedure. Like we will find the maximum first at your average daily demand. Okay, so here they have done it. They have done it combinedly. So here, see, first of all, your population into they have done maximum daily demand. So extra also you can find out. Like if you find out the average daily demand, then your formula will be okay. If you find out the average, wait. If you find out the average daily demand first, then the formula was population into your per capita demand. Yes, population into your per capita demand. Yes, so population it is already given to be 50,000. Per capita demand is given it to be 180, isn't it? Here first you multiplied, okay, whatever answer you will get, then if you multiply it by 1.8, then you will get the maximum water demand. So it is, they have done it combinedly, so same thing. Okay, they are just utilizing their time. You can also utilize like that. You can do in a one step procedure. Okay, then you will directly get the maximum water demand. Clear? So now here we need to find out per hour. Okay, we need to find in per hour, so they have divided by 24. So it is your 675 into 10 to the power 3 liters per hour. Okay, then rate of filtration, it is given it to be 5,000 liters. It is given in the question. Then area, you can find out the area of the filter beds. You can find out the water demand divided by rate of filtration, as we have done in your previous numerical. So your water demand is your 675, we already got, and your rate of filtration is 5,000. So you got the area to be 135 square meter. Okay, so since in the question it is given to find out to design a set of rapid gravity filters. So as I said, that means a set is given. That means you need to divide it by 2. If you need to find it, find the area for each unit. Okay, in your snow sand filter question, it was mentioned that there are 6 units, but here it is not mentioned that there are 6 units or 5 units. Okay, so here it is mentioned in the question that you need to design for a set of rapid gravity filters. That means you have to know that there are 2 rapid gravity filters, and we need to now find out the area for each unit. That means we need to divide it by the total area divided by 2. Okay, then you got the area for each unit as your 67.5 square meter. Okay, now same thing. Okay, if in rapid gravity filter, one more thing you can note it down, this one. If your length is not given, okay, if your length is not given, you can assume the length to be 1.5 times of your width. Okay, you can assume it to be 1.5 times of your width. Then using this, you can the same procedure. Okay, you need to find out the length and breadth. Clear? So it's a very easy numerical. Both are same. Both are nearly it's same. Okay, the procedure. Okay, then this class will now end now. I hope you have understood the numericals. Okay, so once you have understood, if you do again in your copy, then it will be easy for you. Okay, then you will understand it better when you do it by your own in your copy. Okay, okay, then you join by 9:15. Okay, everyone, you join by 9:15. Oh, sorry, not 9:50. That's why I'm thinking 10:15. Okay, you join by 10:15, everyone.